other stars around the universe, our sun is really not that big. In fact, by universal standards, our sun is listed as a small to average-sized star. But for us here on Earth, the sun is the perfect size and distance from us to sustain life as we know it. If you look back through recorded time, you can see how primitive cultures viewed the sun. It was seen as more than just a life-giving force, but was considered a deity by many of these primitive agrarian communities. For these early cultures, the sun was an all-powerful god that helped the crops grow and dominated daily life. Of course, today, the idea of the sun as a deity is no longer a widely held religious belief, but the sun is still worshipped by millions of modern humans during warm months. As soon as the weather is warm enough, beaches around the world are crowded with sun worshippers working on their tans and lounging in the sunshine. While this behavior was once seen as virtually harmless, the world has become more educated, and we now understand the sun can be harmful as well. The sun, for all its benefits, daily rains down on Earth dangerous skin cancer-causing ultraviolet rays. We can protect ourselves with a healthy dose of sunscreen, but nothing works as well at protecting us from the sun's ultraviolet rays than the Earth's own ozone layer. Earth's stratospheric ozone layer is a belt of naturally occurring ozone gas that sits 10 to 30 miles above Earth and serves as a shield from the harmful ultraviolet radiation emitted by the sun. This layer filters out harmful sun rays, including a type of sunlight called ultraviolet B. Exposure to ultraviolet B has been linked to cataracts and skin cancer, and has also been linked to crop injury and damage to ocean plant life. Clearly, it is vitally important for all life on Earth to assure that the ozone layer continues working optimally. Because this layer is so important, it came as a great shock to scientists in the 1970s and 80s when they found that the ozone layer was in fact being damaged in some way. Scientists around the world began to see a shift in our atmosphere, finding that in some places our ozone layer was disappearing at a rapid rate. It found that the main culprit for this rapidly diminishing ozone layer was a man-made substance called chlorofluorocarbon, or CFCs. With alarm bells sounding, the worldwide community acted, and in 1987 produced the Montreal Protocol, which was designed to protect the ozone layer by phasing out the production of substances responsible for ozone depletion. It was also determined that we would need to monitor the Earth's ozone levels to better understand what was going on in the stratosphere. Since the original discovery of the ozone problem, NASA has led the world in monitoring the ozone layer. On today's episode of NASA X, we'll look back at some of those earlier missions and also explore the latest mission to monitor the ozone, called SAGE-3. We will follow the SAGE-3 team through the test phase to better understand how this mission will work and what we can expect when it is launched. We'll also get a better understanding of our fragile atmosphere and what we need to do to safeguard it for future generations. Here in this clean room at NASA Langley, researchers are preparing to launch a science instrument that will undoubtedly affect the lives of virtually everyone on Earth, even though most people know nothing about it. It is called SAGE-3, which stands for Stratospheric, Aerosol, and Gas Experiment, and its main goal is to monitor the Earth's thin, protective ozone layer. Although you might not spend much time thinking about the ozone layer, every day, year after year, it is above us in the stratosphere, helping to filter out the sun's harmful UV rays. In fact, researchers have found that even a 1% change in ozone layer can lead to a 4% increase in skin cancer. Until a few decades ago, not much was known about the ozone layer, but that started to change in the mid-70s. As researchers began studying aircraft flying at high altitudes, they began to worry about the chemicals and aerosols they were leaving in the ozone layer.
The problem started with actually with supersonic transport, where there were some scientists who thought that the gases that were coming out of the back end of those high-flying aircraft, which would be up in the stratosphere, which is a fragile area, very little cleansing takes place, very little water vapor, and that's where the bulk of the ozone resides. And so they were worried about the oxides of nitrogen and their effect on ozone. So that was like in the 70s, 74, 75, right in there. People started to do things and write papers.
The papers that started coming out showed that human activity was in fact changing the ozone layer. To help increase our understanding, experiments were developed by NASA that could help us look into our high atmosphere and determine what was going on. One of the first experiments developed was called SAM, or Stratospheric Aerosol Measurement Experiment. This experiment was developed and flown on the Apollo-Soyuz flight and was the precursor for the future SAGE experiments.
This was an instrument called SAM, Stratospheric Aerosol Monitor. It was flown on Apollo-Soyuz in 1974, I believe. And the way it works, it's a one-channel instrument, looks at 1 micron light, so in the near infrared. And it's a simple little device. They would clip this into the window of the command module, and then Deke Slayton, the pilot of that mission, would take control of the spacecraft, and he would orient it so that it was looking exactly at the sun, using this gun sight, if you will, a forward sight, and then projecting the shadow of that from the sun onto this reticle in the back. He'd center that up, and then he would put the spacecraft into inertial mode, and it would just stay there pointing at the sun as it went into eclipse. And this was what we used to do the first proof of concept that we could do occultation and get information on aerosols. This quickly led to SAM-2, which was an instrument that had one channel, but was the first one to really employ the technique that we use, where we have a scan mirror that effectively scans this across the sun as it sets. And that's how we get our extraordinarily accurate altitude registration that is the hallmark of the SAGE technique.
So we got SAM-2, that flew for 16 years. But the orbit was such, it's a high noon sun sink, meaning it comes over the equator at high noon or midnight, and therefore the occultations are all either in the Arctic or the Antarctic. So that's good, but it's not going to give you a global perspective.
After the 2 SAM missions, NASA developed the SAGE-1 mission that flew in 1978. This new satellite system added several new instruments for measurements and was working well, developing a global database that helped the understanding of global trends in stratospheric ozone. Unfortunately, after only 3 years in orbit, the power system on the satellite failed, leaving the still functioning instrument unable to continue. The next instrument was called SAGE-2, and unlike the mission before it, it lasted nearly 21 years and was crucial in confirming that human-driven activities were changing the ozone layer. In fact, the damage was so significant that researchers found a large hole in the ozone layer over Antarctica.
But the ozone hole discovery really caught everybody flat-footed. And that was in '85, a paper by Joe Farman, British Antarctic Survey. He measured ozone column during the year, every month. And he noticed from the late 70s, all of a sudden the ozone column kept decreasing. The monthly column of ozone above the Antarctic was going down drastically in the month of August. In September, then October, it would come back. And so, as a good experimentalist, what Joe did was he went and tested his instrument, took it out to Boulder, Colorado, where the standard instrument of that type was, compared to it. Everything was fine, and so he wrote a paper in Nature which tied chlorine, chlorofluorocarbons, chlorine in the stratosphere to ozone reduction. he was finding chlorofluorocarbons everywhere. So Joe tied these two things together and guessed right. So the dynamicists thought it had to be dynamics, photochemists thought it was photochemistry, and the race was on, and the chemical manufacturers got involved. So that phenomenon was something very new in terms of what it did, and it pulled the entire world together, including the chlorofluorocarbon manufacturers.
Scientists around the world began looking at all the data and quickly determined that immediate action had to be taken to stop this ever-expanding hole in the ozone layer.
After we did our detective work and demonstrated scientifically that it was chlorine that was the problem, they went ahead and presented that to all of the various governments around the world, and the outcome of that was the Montreal Protocol, which was a treaty signed by virtually everyone on the planet that was designed to protect the ozone layer by limiting the use of, or in some cases banning, certain chemicals. It was signed in '87, went into effect in '89. Chlorine peaked in roughly 1997, and data from SAGE 2, which was the precursor to SAGE 3, the very long-lived mission, 21 years, showed clearly that when chlorine peaked, the ozone stopped declining, and there's some hints of it starting to recover. That mission ended in 2005. So with SAGE 3, we're going to be coming on here in the 2016 timeframe through 2020, and the expectation from models is that we'll be in a period of recovery. We should have recovered roughly half of the ozone that we lost from 1980 to 1997. So that's why we're doing this mission, is to figure out what the pattern of recovery is, whether the models are showing the same pattern of recovery. If they're not, what subtle things are they getting wrong in their model that will help improve their ability to predict future changes.
In 2001, the third generation of SAGE experiments, called SAGE 3, was built. Planning ahead, researchers built 3 identical instruments that could all be used to measure the atmosphere. The first of these SAGE 3 instruments was launched on a Russian Meteor 3M spacecraft in 2001. Unfortunately, it only lasted until 2006, again due to a power supply issue, not to any defect in the instrument. Planning began on the next mission, but this time, rather than rely on an unmanned satellite, this SAGE 3 instrument will fly on the International Space Station.
We built 3 SAGE 3 instruments, and this is the instrument, or a mock-up of the instrument we built for the International Space Station. That's where this is going. We flew one with the Russians back in 2001 it launched. Operated for 5 years, and so we're pulling this one out, fly on the station now to go ahead and extend that data record. SAGE 2 flew before that, lasted over 20 years, a completely impressive data record. And so the international community is very familiar with these measurements, and so SAGE 3 on the space station is going to extend that data record. The nice thing about that is that the instrument is essentially self-calibrating, and so we can look at one SAGE to another SAGE without any biases in the measurements, and that's the data that the science community needs.
You can fly one instrument, have a gap, fly another instrument with different technology, roughly the same wavelengths, but different technology, and you can quickly compare those two, link them together, even though there's a gap there. Normally what you want with an instrument or a measurement series is you want to have one, fly another, that before that one ends, have some overlap so you can compare and then fly that, and so you piecemeal these things together. But with SAGE, because of the technique that we use, we just have to find one number, basically, to line these data sets up globally. That's a unique characteristic that's specific to this technique.
The technique that has been used by each of the previous missions and will again be used for SAGE 3 is called occultation. The astronomical definition is the temporary disappearance of one celestial body as it moves out of sight behind another body. In this case, SAGE 3 will be in orbit around the Earth, with its instruments pointed toward the Sun. As it rotates around the Earth's shadow occults or blocks the Sun.
The science is looking at the Sun or the Moon and using that, essentially that backlight to illuminate the atmosphere and allow you to scan it and look at the different chemistry and composition of the atmosphere in a really good vertical profile, because you're looking at that really strong source that's backlighting the atmosphere, and you're scanning through the atmosphere back and forth, and it allows you to look at things like ozone, which has been a product of SAGE going back, all the way to the beginning, to things like aerosols. That's another big component lately. SAGE 3 was designed, this version of the instrument was designed to be able to pick up channels that would give us aerosol data. So when you have something like a volcano go off, it throws a bunch of particles, what are called aerosols, into the atmosphere, we can see that. Something like things like optical density can be derived from the data that SAGE provides.
Although this instrument was originally built in the 1990s, some major hardware has been updated to make certain it can handle a modern workload. One of these new pieces is called the hexapod, and it was built and delivered by the European Space Agency to help point the science instrument in the right direction.
One of the things that, working with space station, it's not as stable, constantly stable as a free-flying spacecraft. It has to be able to move at such a large structure, and it has to accommodate various attitudes because of visiting vehicles, and they occasionally have to reboost their altitude. So to be able to accommodate that varying attitude, it was conceived even back in the early 2000s that we would need some kind of pointing platform. And so there was an agreement struck with the European Space Agency to provide that course pointing platform, and that's what the hexapod is, and that was delivered earlier in February of 2015 from Thales Alenia Space in Italy, under contract to ESA. So that provides us point and control, so that we can take the sensor and point it directly at the Earth, and then be able to look off to the limb to where the Sun and the Moon set and rise. There was a whole parallel effort to come up with the rest of the equipment that was needed to actually make it work on space station, and that's been the bulk of the effort, I'd say, for the last 2.5 years. Designing, building, testing those individual subcomponents. We had a whole new subsystem called the Interface Adapter Module, which is essentially the brains and memory for the payload. It interfaces the space station, provides power distribution, records all the science data for downlink to the ground. That whole unit was brand new. It was basically designed from the ground up.
There are also 2 contamination monitoring packages that allow the team to monitor and react to contaminants coming from the space station. And finally, a disturbance monitoring package that detects vibrations on the space station.
And then all that whole instrument payload gets connected robotically to our second payload, which was really something that came about as an accommodation for flying on the space station in 2015, as opposed to the early part of the century. We originally designed the heritage hardware, the instrument and the hexapod, to fly directly pointed at the Earth to start. And the mounting locations on space station that are available in 2015 did not have that native view, so we had to develop a way to get that view that we needed, and that's where we came up with what's been referred to as a fancy 90-degree bracket, but we call it the nadir viewing platform. And it replicates that interface at 90 degrees and allows our second payload to be attached to it robotically. So we actually fly up as 2 separate payloads. We install the nadir viewing platform payload, and then we install the instrument payload to the nadir viewing platform.
Once this massive undertaking is complete, it is then up to the spectrometer on SAGE 3 to start analyzing data and begin downlinking it to the team on the ground. In typical NASA fashion, all of this data will be shared with researchers around the world, who in turn will share the information with policymakers and people within the general public. All this data is important because it helps us understand how we can better protect the planet.
Human activity on the planet has gotten to the scale where we're impacting our environment, whether it's deforestation in the Amazon, pollution in local rivers, or pumping things into the atmosphere. We need to keep track. It's our responsibility to keep track of the effects of those impacts.
Obviously, the ozone layer is something that protects us from UV radiation. It affects things, how much sunscreen we have to wear. So there's a lot of effects for the average citizen. They may not see it directly, but ultimately the data that comes out of something like SAGE drives policy decisions by the U.S. Congress.
One of the nice things about working at NASA and working on this project in particular is everybody realizes that this could have, a lot of importance beyond just what you're doing on a, say, like a normal job. And I've been fortunate in my career to go ahead and actually kind of see how important the data is with the scientific community and the value of it. And I think that's a great motivator. I mean, we have a wonderful team working on this project, and I think one of the reasons that they work so hard and they're so motivated is that doing this is adding the value as you suggest, and it's important not just to us, but to my children and my children's grandchildren. So there's a lot of power in being able to work on something that's so beneficial.
It is clear that this team is working hard to continue the tradition of excellence left by other SAGE missions. It is also clear that their efforts will undoubtedly affect the lives of all of us back here on the planet.